Okay, so 9 a.m. and let's continue. All right, so where we are. In the previous classes, recitation classes and lectures, we practice how to find magnetic fields. Basically, like a field production. We were involved in field production, right? And we introduced two fundamental laws which can be used to find magnetic fields: Biot-Savart law and Ampere's law, right? Both fundamentals. But of course, it's not the complete story in order to describe what we observe around us, right? Because, yeah, let's say you produce yeah, ah, sorry, somebody's mic is on. Sorry. All right. But of course, those fields, once you produce them, of course, they are not in empty universe, right? So there are some objects which are exposed to that magnetic field, right? And of course, these objects are going to, or these fields are going to interact with these objects, right? So we need to introduce quantity which is going to describe interactions of those magnetic fields with objects. Interactions, which quantity I'm talking about? Force. And of course, since the nature of this force is going to be magnetic, so we're going to call this as a magnetic force, right? And of course, we need to introduce a fundamental equation, right? Which can be used to describe interactions with any other objects, right? And since we know that any objects, any material consists inside, if you dive inside, of course, you will see that it consists of tons of positive charges, protons, and tons of negative charges, electrons, right? So if we, for example, can write down an expression for a magnetic force acting on a point charge, that will be the fundamental equation. And then using some logic, some complicated analysis, we can describe interactions of the field, of a field with any complicated object, more complicated than a point charge. But the fundamental equation, a magnetic force acting on the point charge. So today we're going to, in next class, we're going to describe interactions, forces, magnetic forces, right? So what we have, so that's what I wrote, right? And we're going to play with two systems: point charge and current. Okay, so let's start with the point charge. What is if you have point charge Q, you see, flies, moves with velocity v, and as it moves, it is exposed to the magnetic field B. Okay, of course they're going to interact, and we introduce the formula, which is the fundamental law, right? Cannot be derived. It is accepted as an axiom, basically, right? Written based on observations. Okay, so we wrote it down in the lecture. So F equals the value of the charge, and then cross product between the velocity of the charge and the magnetic field. This is one of the fundamental equations in physics and, of course, in electromagnetism. Okay, so it was, of course, framing it. You know what? Too much of blue and red. Let me change it. Right. And, of course, so if you want to apply it, it will consist of two steps, right? So first, you will find the magnitude, U, V, B, and times sine of angle between them. So that's the magnitude. And then direction, 1.5 steps in order to find direction. First, you apply right-hand rule number 1 to find direction of this cross product. But that's not the whole story. After that, you need to have a quick look at the charge. If charge is positive, then that direction is the correct direction for the force. But if charge is negative, then you need to take that direction and flip it. Okay, so then direction, you apply right-hand rule number 1 plus sine of Q. So that's how we're going to apply that formula. Okay, so yeah, that's the fundamental equation. And then this formula can be used to derive So now the next formula is not fundamental, but very practical, right? Lots of, very often we use that formula, right? If you have a wire, it doesn't have to be straight for now, and of course with current, let's assume that is the current direction, and let's assume it is exposed to the magnetic field. Magnetic field doesn't have to be uniform at this particular moment, right? Of course, since current consists of bunch of charges drifting in the same direction, of course they are going to experience magnetic force, and of course there will be magnetic force acting on the whole wire. Okay, so how can we find it? How can we write it? Of course, we need to write the force on an infinitesimally short section of that wire. Why? Because different sections of the wire will be under different conditions, right? So we need to take infinitesimally small, and write formula for that. Okay, so the formula. It's a force, okay, let me write it here, dF. dF because it's some force acting on this small section dl. Okay, it will be like here, it's a current, right? And then the cross product of dl and magnetic field, right? So one small thing, dl is presented as a vector. What determines its direction? Current. Direction of the current determines direction of this dl. And again, I told you up to this point, the author of this book used ds all the time to denote these segments, but now dl. Again, it's not completely bad, but it doesn't sound cool, right? Usually in the book, if you decided to use a certain symbol, you should use it throughout the whole book, right? It's not cool. Right. Yeah, and of course, in this case, finding direction of the force is simpler, just a cross product, because current cannot be negative. It's a value of the current, can be only positive. So in this case, it's easier, just dl cross b, just one step. Here we had 1.5 steps. Okay, so let me check if I mentioned everything which I was planning. Yeah. Yeah. So, but using this formula is complicated. Every time we have to do integration, right? So, but if you apply this formula for a straight wire with current I, and if length L of that wire, this wire can be infinitely long, but for example, what if length L only exposed to the magnetic field? Then we can write the net force acting on this section of the wire, which is exposed to the magnetic field. It's a trivial, and we're going to assume that our magnetic field along the wire is the same. Basically, we can say uniform magnetic field, right? In this case, integration is trivial because this is constant, and then you just integrate dl, it will give you L. So this transition is trivial, so I can write immediately the formula. So F equals value of the current, and then L. Again, you see, I write this length L as a vector. And again, current I determines direction of that L. Cross B. That's what we're going to use most of the time. This formula and that formula, because application of that formula will require integration and more complicated. Right. Okay, so that's what we need for today's class. And now let's start rolling. First, again, as usual, at any moment, stop me, say something, right? If you started getting lost. First problem 26. It's still chapter 29, right? Let me write it here. So 26 problem. So what do we have here? Proton flies through a magnetic field. Magnetic field is given, the value of the magnetic field and direction is given. And we need to find the force acting. Actually, this problem is quite straightforward, just direct application of the formula. Right? So let me draw first the situation. Probably I will do it here. It should be enough. So let's say this is x direction. this is Z, you see, Z, up Z-axis I positioned, right? And then Y-axis, okay, I will use a right-handed system, so Y-axis will be into the board. Into the board, it's a cross. So that will be Y-axis. Right. It's just for our problem, this orientation of axis are more convenient because our particle is going to fly in the XZ plane. Right. That's why I sort of turn coordinate system in position in this way. So then, magnetic field. Magnetic field acts this way. So that's B. It's uniform. So the value of B, okay, first let me write, so we have a proton. Wait. Right, proton flies through B. Okay, so B is given and it's along x-axis, absolute value is 0.5 and it acts in the x direction. You see 0.5 I hat. Hat means a unit vector. Right, 0.5, yeah. And of course units of magnetic field at Tesla. Then a proton flies, okay, so let's say this is my proton, right? And it flies in the xz plane in this direction. So that's V. The value of V, I don't remember, it's, okay, I can fit it here. V equals 1 times 10 to the power of 7 meters per second. 10 to the power of 7. And this angle theta is 45 degrees. Between the x-axis and the direction of velocity. Okay, so we need to find force. That's it. That's what is given. Yeah, nothing else, of course. So we need to find F, of course, on the charge. Physics, again, as usual, first of all, you need to realize the physics. Physics is trivial, right? Basically, on the fundamental level, we have a charge which flies, right? Again, yeah, I forgot to mention. So you see, again, as I mentioned in the lecture, in the world of magnetism, everything is in dynamics. So for a charge to experience magnetic force, that charge must fly. If you have stationary charge exposed to it, doesn't matter how strong magnetic field, the charge wouldn't experience, or the charge wouldn't experience any force. So it must move. Right. Right. So in this case, so we have here charge which moves, exposed to the magnetic field. Then, based on our observations, of course, it will experience the force, and we model that force using that formula, fundamental law. That's it. So in terms of physics, not much to discuss. So we'll just, let me just separate it like this and start with the formula, rewriting fundamental law. Formula sounds so kind of not cool, but fundamental law, it sounds great, right? So V cross B, right? Okay, and 2 steps, magnitude and then direction. So what? Probably I will start with. Let me start with a direction. Direction. Right. So right-hand rule. V cross B. First align your hand along V direction, so that's that way, right? But then you need to orient your hand and position like this, so that you can naturally bend your fingers along the second vector in the cross product, so sort of like this, right? And as a result, your thumb will give you the correct direction for the force. For the cross product, V cross B only, not for the force, right? So that into the board, then you need to check quickly the sign of the charge. We are working with the proton, so positive charge. So it means that that is the correct direction. Direction of the cross product gives us a correct direction for the magnetic force, right? So let me write. So right hand rule number 1, and so plus charge is positive. Okay, let me just write in the brackets just to remind you that, of course, don't forget to check the sign. And as a result, force is, which way I wrote it? F is in plus y hat direction into the board. That's our positive y direction, right? So now we know the direction. And now let's find the magnitude. So now magnitude. All right, so F, so now you see there is no vector sign on top. So it means that's magnitude. It will be Q, V, B, and sine of the correct angle. Right? Is this the correct angle for the cross product? Of course it does. Okay, it is. Right? Because what you remember, the tails of both vectors must be positioned at the same point, and that's what we have in the diagram. Right? B and tail of V are at the same point, so that is the correct angle. So we can use our theta, which is 45 degrees. Charge of the proton, it's the same as charge of an electron, but positive. V is given, B is given. 45 degrees is also given. Right. So you can easily calculate it through, right? And you will end up with what's the number? 5.7 times 10 to the power of minus 13 units. It's just a force. Of course, nature is different. Nature is magnetic, but it doesn't matter. We use the same units, right? So it doesn't matter if it's some mechanical force, electric force, magnetic force. It's just a force, units of Newton. Pushing, pulling, right? Okay, so now as a result, we can write using components in a component form. So let me write down F. You see now I put the vector sign on top. Now it's a vector. So X component 0, because we just found that the whole force in the y direction. So then a y component 5.7 times 10 to the power of minus 13 newtons. And again, z component will be also 0 because the force is in the y direction only, right? Or you can use I hat, j hat, k hat, right? So use that notation. It's not a big deal. So you see, the problem is pretty much it's a practice how to use that formula. That's it, right? Not much to discuss, right? But of course, it's worth of looking at the problem like this at least once. More than once is a waste of time, should be. This also part of your homework. You will have, it's a part A, but there is also part B. Right? This is part A. If some of you know how to use a determinant method to calculate the cross product, okay, use that. Not a big deal. There are different ways of finding the cross product. So use whatever. It depends on your level of math. This is the simplest probably. So now next, okay, if you have questions again at any moment. The next, what if we, okay, it's not a problem. It's sort of like an introduction to the next problem. I just want to increase complexity in steps. First, let's look at this system. What if we have two long wires with current parallel to each other? Oh, current, I think current is, okay, in this case, current in the same direction. Infinitely long, right? But we will have to find, we want to find the magnetic force on the length L of one of these wires. Only on the length L. Right? Because if you try to find the net force acting on an infinitely long straight wire, of course you will end up with infinity, right? But of course, in real life, nothing is infinite. Every time we just can model some long objects as being infinite, right? But again, it's the way we model it. So let me just put a new bullet over here, because it's not a problem from the book. And we have two wires. Okay, let me probably use different colors, right? So let's say this is the wire number 1. Okay, I will use blue. And then green will be here. And currents. This is I2, and this is I1. Numbers are not given. I want to discuss the procedure, the strategy to address problems like this. Numbers you can easily, if you want, you can easily add, right? It's not the goal. All right, then what else? Yeah. As I said, they're basically infinitely long, but we want to find the force acting on this wire I2 of length L. All right. Okay, so let me show that this length is L. Right. What else? D is given, spacing between, distance between these two wires, right? So D. So let me write what is given. Two parallel wires, I1, I2, right? And then what else given? L and D. So what we need to find? We need to find force on I2 of on I2. I'm just thinking of phrasing of length L. Okay, yeah. It should be clear enough. Okay. Right. But of course, these two wires, they're infinitely long. But we want to find force acting on a certain section of length L. Right. Okay, so that's the situation. And first of all, we need to realize how we're going to address it, right? The procedure. Look at the formula. Of course, we will have to use this formula because it's a force acting on the wire infinitely long, okay, on a wire of length L, right? So, and straight wire, yeah, that's the key word, straight. So we will have to use this. But look, here magnetic field is given. We assume that magnetic field is given, right? And then current I of length L is exposed to that magnetic field. In our situation, magnetic field is not given, right? And in this formula, force is exerted on what? On the current of length L, right? So in our case, we know that we want to find the force on I2. So that's our object which experiences a force. Okay, the force, right? So it's this current I of length L, I2. But magnetic field is not given in our situation. So we need to, of course, realize what creates this magnetic field in our case. And it's obviously current I1 is going to create magnetic field. So this is a source. Okay, let's use the source of the magnetic field. And then wire I2 is exposed to that magnetic field. So I2 will create this magnetic field. And I1, it's an object on which force is exerted, right? If the question was opposite, find the force on I1, so then I1 will be over here, this IL, right? Oops. And magnetic field would be created by I2, right? Of course, in both cases, magnitude of the force will be the same. Because of what? Newton's third law, right? If this object exerts force, let's say 5 newtons, then this object will exert the same force, 5 newtons, on this one, right? Newton's third law. But since in our case, we want to find the net force on I2, so this is the object on which force is being exerted. This is the source of the magnetic field. So first, let's find the magnetic field, which will be used here, and then of course we will have to use this formula, right? So that's what I wanted to discuss, which object is an object on which force is exerted, and which object is a source of the magnetic field. Source, object. Right, okay, so now, okay, I wrote what needs to be found. Okay, and now let me write what I just told you. In this case, I1 is a source of B, is the source of a magnetic field. And of course, since it's related for the first wire, so let me put the subscript B1, right? And let's find direction of that magnetic field B1. Right-hand rule number 2. Outstretch your thumb in the direction of the current and curl your fingers around the wire. So it means that on this side of the wire I1, magnetic field will be into the board. It's a cross. Right, so cross, and of course I can draw it here, cross. So that's B1, right? On the other side of the wire, of course, I can also draw it. We don't need it, but let me draw it anyway. So this will be B1, of course, with a dot. So B1. So, and can we write down the magnitude of this magnetic field? Easily. From the previous class, it's an infinitely long straight wire, right? So mu naught I1 divided by 2 pi r. But since we will need the value of the field at the point where the wire is, this wire I2. Of course, we need to write expression for the magnetic field for this distance d. So let me write immediately. So the value of B1 will be equal to mu naught times I1 divided by 2 pi d. So it's which way I wrote it? Okay, at the place of the wire 2, right? So instead of r, I wrote down d, which is the distance between the wires. So that's the value of the magnetic field at the place of wire 2. Direction into the board. Okay, let me write direction into the board. And I already showed it on the picture. Right. So after this step, once you know the value of the magnetic field and its direction, you can forget about I1. Now we have its representative magnetic field. So now it's pretty much, now we can just use this formula, nothing else. So now we know the magnetic field and we know the wire which is exposed to that magnetic field. So now we can forget about this wire I1, right? So now at this point, we just need to use the formula. Okay, it's the first step, right? And the second, now I2 is exposed to B1, right? Is exposed to B1 and of course experiences force. Okay, let me write underneath. So as a result, F. Okay, I will write F2 since it's a force on the second wire. F2. Right. So it will be I. Which subscript we have to use? I see sometimes mess at this point. Which subscript? Since we're trying to find the force acting on wire I2, of course I2. Of course, here should be I2. Then L cross B1, right? So that's, and now again I will use in two steps. First, let me find magnitude and then direction. Maybe first direction and then magnitude, right? Yeah, let me do first direction, for example. Right. So first direction of F2, right? Right hand rule. One step. L, again, direction of L is determined by the direction of I2, current I2. Okay, let me write that. Direction of L is determined by I2. Direction of L is determined by I2, right? Like I explained to you over here, right? Okay, so direction of L, up, right? Because that's the direction of I2. Magnetic field B1 is into the board. So L cross B, right? L cross B. And my magnetic force, direction of the force is to the left. To the left. So it will be force of attraction. Okay, so let me draw this force. So that will be F2. So I will write right hand rule. And okay, number one. So it gives us to the left. Oops. My soccer ball flew away. Okay, yeah, it's worth of framing because it's part of the answer, to the left. And now the magnitude. So that was the first bullet. Now the second, magnitude. Okay, so now let's write explicitly. So F2 equals the value of I2. And then the cross product, it's a magnitude of the first times magnitude of the second vector times sine of angle between them, right? Cross product. We've practiced it already many times. So L B1 n times sine of angle. Okay. Which angle? Look at the picture carefully. Which angle is the correct angle? So direction of L, it's a direction of I2. Direction of L is up. Direction of the magnetic field, B1, is into the board. So up and into the board, it's a 90 degrees, right? That's our situation. Okay, let me turn it. You see 90 degrees. B is into the board, L is up. So 90 degrees. Sine of 90 degrees is 1, right? And so now we just need to grab this B1 and plug it into the this expression for the force, and that will be the answer. So now let me rewrite it. So it will be I2L mu naught I1 divided by 2 pi d. And sine of 90 degrees is 1. Okay, let me emphasize on that. So this is equal to 1. Yeah, so that's the answer, but let me just rewrite it in a nice way. Right. So it will be mu naught I1, I2, product of the currents, divided by 2 pi d, distance between the wires, and L, length. Right. So that's the expression for the force. Let me write it like this. So F2 and frame this end. So that will be the answer. That will be the value of the force acting on the wire I2. Quite often, because yeah, these are infinitely long wires. Quite often, people use in research, right? You will see at some points probably of your life, right? So units, I mean, force per unit length is used in these cases quite often, right? Force per unit length. In this case, you just move this L to that side, and that will be the force per unit length. That's what is used most of the time for very long objects. Right? or let me write the force per unit length, per unit length. So it will be F2 divided by L, and you just rewrite everything without L. So it's a mu naught I1 I2 divided by 2 pi d. Yeah, if you have a system, yeah, we have plenty of situations where we have two long wires next to each other. All right, and if you want to describe those interactions, usually people use force per unit length, right? So that's how you can get this. So introduce first some finite distance, calculate for that finite distance, and then divide the answer by that distance. Again, every time in the problems like this, you need to realize in your head which object is an object on which force is exerted. In our case, it's I2. And the second object is a source of the magnetic field. Right? Right. Okay. So again, if something not clear, tell me. All right. Otherwise, I will move to the next part, and let's increase complexity. In which way? Let's add the third wire. Instead of two wires, let's say we have three wires, and actually this is the problem from your homework, right? Right. So there are three wires, and in the homework you will have to find the net force acting on each of those wires. Part A on wire 1, then on wire 2, and then on wire number 3. Here we will just solve a one case. Right. We will find the net force on one of those wires. Okay, so now I need to probably invade this part of my whiteboard. I need to erase this. A new marker, difficult to erase. Okay, you see some dark area. So it's a problem 36, 29, 40, 36. All right, 29, 36. So that's the problem. And as I said, there are three wires. Okay, I will probably draw them like this. First, the top one will be the black one. All right. I'm just trying to estimate the amount of space that I might need. Right. Of course, with current I1. The values of currents the same, 10 amps, but of course I need to use different symbols, I1, I2, and I3, so that we will know which current we're working with, right? Then I2 will be, okay, blue. Let's say it will be here. And current this way. So that's I2, second wire. And the last one, the third one, and they are at the same distances. But of course, I will still use different symbols, because we need to know which current, okay, which distance is being used. Right. And this flows this way. So this is I sub 3. So that's the electrical part. And now distances. This distance A. Okay, I will write there the values A. And this distance is B. So we have I1 equals to I2 equals to I3 equals to 10 amps. And A equals to B equals to 2 centimeters. But of course, you understand that at a certain point, we will have to convert them to meters. So I will do it right now. So A equals to B equals to 2 centimeters equals to 2 times 10 to the power of minus 2 meters. Let me check what else if I missed anything. Yeah, this part quite often I missed. Okay, it's good that I looked at my notes. Again, these are infinitely long wires like in this case, but we will have to find force acting in part A on this wire I1 of a given length L. Right, so yeah, it's basically extension of this problem, but we added the wire number 3. So I just increase complexity step by step, right? So that's why I started with that one. Right. Okay, of length L, so let me draw it here underneath. L. And L is 50 centimeters. So 0.5 meters. Okay, so that's what is given. And in part A, we need to find force on the first wire, on the top wire, on the top, acting on the top wire. Okay, so now I gave you everything. All my heart, right? If you care about small things, right? Small gift. Okay, so what? First of all, let's discuss again the strategy. And strategy is like that. First, you need to realize, of course, since we want to find the force on the wire, on the straight wire, of course, at the end, we will have to use this formula, right? Formula giving us the force acting on the straight wire. But again, magnetic field is not given, right? So I1 it's this, right? And then magnetic field is created by what? By wire number 2 and wire number 3. So this is an object on which force is exerted. This is the source of the magnetic field, and this is the source of the magnetic field in part A. But in part B, which is again in your homework, this will be the object on which the force will be exerted, and you will need to find that force. So now then in that case, I2 will be this, and magnetic field will be created by these two wires. So first that wire will create magnetic field at this point, and this wire will create magnetic field. Of course, you will have to find the net force, right? Then the last part C, you will have to find the force on I3. So in this case, this will be an object on which the force is exerted. And this will create magnetic field, and this will create magnetic field. Superposition of two fields, right? Okay, so, but in our case, this is the object which experiences the force, and this is source of the magnetic field, and this is a source of the magnetic field. So now, what else I need to add? Yeah, this is given, a given F1, all right. Okay, yeah, let me write this, what I just told you. So, which way I wrote it? I1 is exposed. So let me first write I2 and I3 are sources of okay, let me write of B net, let me write like this, of B net. Of course, this B net consists of two parts, B1 and, B2 and B3, right? And then I1 is exposed to B net, and of course experiencing the force. Since it will be exposed to magnetic field, it will experience the force, right? Okay, so now, like here, it was simple because we had only one source, so we wrote only one formula, but now, of course, we need to write formulas like this 2 times for B2 and for B3, right? But first, let's draw directions, right? You know what? Let me do right. So do it this way. So first, let's start with B2. B2 magnitude, it will be mu naught, the same formula, mu naught I divided by 2 pi r. And of course, in our case, we will need to know the magnetic field at the place of wire I1. So we will have to use distance A, right, in order to write the magnetic field created by the wire number 2, right? So it will be mu naught times I2 and divided by 2 pi A. Because again, we need to know the values of the magnetic field, like here at the place where in our case, the first wire is. And let me write direction. Direction can be found using right-hand rule number 2. Outstretch your thumb in the direction of the current, and then curl your fingers around the wire I2. So above the wire, magnetic field is into the board, cross. So here we will have cross. Of course, for your homework, you will also need magnetic field, a value of the magnetic field below blue wire. So of course, below it will be out of the board. So below, out of the board, so it will be dot. So that's B2, B2. And even here I can draw dot B2, right? No, here it will be still cross. Right? So since our wire I1 is above the blue wire, so it's a cross into the board. So let me write just into the board. Into the board. Okay, now let's do the same for the wire number 3. Of course, it creates its own magnetic field at the point where I1 is. So let me write B3 equals mu naught times now I3 divided by 2 pi. Which distance? Now we need to write down here. Distance from the source of the field I3
A
to the
plus B.
point where, yeah, A plus B, of course, A plus B. Right, so it will be A plus B, right? And direction, now let's carefully draw a direction. Sum, curl your fingers around. So above green wire, it will be out of the board dot. So it will be dot, 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 and even here dot, dot. So that's our B. Okay, it's a B1. Over here, still B1, right? Over here, I can write B1. No, B3. Why B1? No, B3. Force of habit, still using the same, right? But below, it will be into the board. So into the board, cross. So that's B3. And here I can draw also cross. Okay, we need this. Out of the board. So it's out of the board. Okay, so and for this formula we need B net. Of course, superposition of two fields at the place of the wire I1. So it will be, and which one is actually stronger, B2 or B3? Of course, B2, right? Why? Because if the source is closer to the point, right? The source is closer, the field is stronger. A is smaller than A plus B. Of course, B2 is larger. So the net field will be along the direction of B2 into the board. Right. Okay, and let me also emphasize, so absolute value of B2 is larger than B3 at wire I1, right? So as a result, I will subtract B3 from B2 because B2 is larger, right? So I can write, so B net equals to B2 minus B3, right? So, and of course, I will factor out immediately mu naught over 2 pi. Mu naught over 2 pi. And what? Cannot be. Okay, let me just quickly. So it will be I2 divided by A minus I3 divided by A plus B, right? And extra minute. Because now what's left? We know the B net. Now we just need to plug into this formula, and that's it. And so we write down the formula, magnitude and direction. So it's a 1.5 minute. So now, right, so F1 equals to which subscript, which I1, because that's the wire which experiences the force I1, and L cross B net, right? Okay, so let's first find the magnitude. Oh no, direction. Let's take care of the direction. Direction. Yeah, and B net, of course, into the board. Into the board. It's determined by the strongest field B2. So B net into the board. L, direction of L is determined by the direction of current, so L that way. Into the board that way, so L cross B, the net force, the force will be up, right? Let me check. Yeah. So the force will be up. So this will be F1, right? So direction, all right, L by B net. So it gives us upward. And then magnitude. So F1 equals to I1 L B net. And the sign of which angle? Between L, which is given by I1, and B. L that way, B is into the board. It's like in the previous problem which I raised. It's 90 degrees, right? 90 degrees. Sine of 90 degrees, right? So, okay, that's the answer. I1, L. And instead of B net, I will just write this formula, which we derived, and that's the answer. Mu naught over 2 pi and I2 divided by A plus I3 divided by A plus B, right? So that's the answer, and direction is upward. So let me frame this and frame this. Okay, let me check. Yeah, of course. Right. Yeah, actually there are numbers. Since there are numbers, let me write down the formula. I mean the answer, 2.5 times 10 to the power of minus 4. It's just the force, newtons. Right. Part B and C I already told you, right? So now the difference will be, this will be the object on which the force is exerted. This creates the field, this creates the field. Part B. For part C, this will be the object on which the force is being exerted, and magnetic field, the net magnetic field, will be created by this wire and that wire, right? Again, properly, you need to find directions properly, right? Okay, guys, sorry for holding, right? I thought I will be able to finish it.